All right, welcome to the last of the first session. And so what I want to do now is I want to talk about some theory of games. And so there's far more slides and far more games here than I was going to be able to do in 40 minutes. But hopefully this will just give you a sense of what's out there, what kind of analysis can be done. And again, if we want to explore any of these further, we do have another class. All right, so tic-tac-toe. So in the old days, I was actually the reigning champion of tic-tac-toe at the elementary school playground. No kid ever beat me, despite many who were confident that they could easily defeat me. So my question to you all is, how many opening moves are there in a tic-tac-toe game, or how many pairs of first two moves are there?
9 opening moves, right?
9 opening moves, and how many responses?
8.
8. So the total is 72 possible pairs of first two moves. If you want to look at 3 moves, that's 9 times 8 times 7. So it's growing very rapidly in terms of how many things you need to analyze. But in this beautiful, well-prepared, well-thought-out, integrated series of lectures that you're listening to today, earlier we talked about pi. You don't have to laugh out loud. You can at least mute for that. So we did talk about possibilities for the Pythagorean formula. And we saw that some would just write out, and one of them, there was a great answer. It wasn't concise, and we boiled it down to it wasn't symmetric. And so over here, if we look at symmetries, I'm going to re-ask the question. Up to symmetry, how many different opening moves are there in tic-tac-toe?
6.
I claim it's even less than 6.
Oh, yeah. 3.
3. So we could go in the corners.
Yep.
We could go in the middles. And we can go in the center. And so if you just rotate the board, you can see that all of the ones are equivalent to each other. Now, if I look at all the different opening moves, there's 3 possibilities. One on the far left, how many responses are there up to symmetry? I know there's 8 responses. Symmetry, how many possibilities?
3?
No.
Well, there's 8
3?
if we don't. I'm sorry?
Would it still be 3?
Yeah.
Well, let's
You
see.
5?
So somebody give me one spot where you could go.
4. Diagonal.
I'm hearing almost every number between and 8.
So we got it.
So can somebody give me one possible response?
Middle.
I'm sorry?
Like the middle square there.
Right, and nothing is symmetric to that. So that's one response.
Mm-hmm.
And in the corner down here, there's nothing like that. That's 2 responses. Where else would you go?
Like right next to it?
Right next to it. And so both of these would be the same if we flip the board about the middle.
Mm-hmm.
So physically, we would have to turn this in 3-dimensional space. We can do that. That's not a big deal for us. But those 2 moves would be equivalent. And so I'm just showing you one possible move on each board. Then here's a second possible move, a third possible move, a fourth possible move, and a 5th possible move. There's really only 12 pairs of first 2 moves. And so I am now sharing with you my patented secret of tic-tac-toe success. There's really only 12 board configurations after the first 2 moves. If you have any students who like science, you can talk a little bit about biology and chemistry. You can use Lego, and you can talk about, if I have some Lego bricks, how many ways can I combine them? Well, what does it mean to have 2 things that are symmetric? Do I have to be able to rotate from one to another in 3 space, or can I flip to the 4th dimension? For stuff on a board here on a plane, we have no problem rotating that in the 3rd dimension. But for some of these chemical compounds, the mirror image actually kills you. So when you're trying to analyze, there's only 12 possibilities. So there's a lot of questions you could ask. Does either player have a good strategy? And the answer is no, tic-tac-toe is boring. If both people have a little bit of experience, the game will end with a draw. So what happens if you play randomly? If you assume that when you move to any open square with equal probability, what's the chance of player 1 winning now? It's actually not hard to write a tic-tac-toe game where you write how the computer responds. And the simplest computer component just goes any square randomly. Then the next smartest computer checks and sees, are there any 2 in a row for the opposition? And if so, I will try to block. And so you can program different levels. The other thing which I love to do as a mathematician is, can I make the game interesting? And there's a lot of different ways to make tic-tac-toe interesting. And so I'm going to talk first about tic-tac-toe and tic-tac-toe. There's 2 different ways to play this. And the rule is that if you move in a square, the next move is determined from the position of the previous. So for instance, let's say that I open by going in the upper right spot in the middle board. What this means is now O has to respond by going somewhere in the upper right grid. Let's say O goes here. Now I have to respond by going in the second row, first column. I have to go somewhere on this board. And now, by stupidly going here, I now force O to go in this board again. O now has 2 in a row. And now it's X's turn. So I go down here for X. That forces O to go down here. O goes in the center. Classic bad move by O. Right?
Yep.
It helps when you can program your opponent's moves. So now that O has gone here in the center, it's X's turn. X has to go somewhere in the center. I see some other people have joined us. Where should X go now in this center?
In the middle.
In the middle. And X gets 3 in a row and wins. So in one version of the game is now over and X has won. In another version of the game, X now controls the center square with a giant X, and you keep playing tic-tac-toe on the giant board. And you keep playing until somebody gets 3 giant X's or 3 giant O's in a row. Now you might be at the point where you've played the game so long that one of the smaller grids is completely filled up. So you have to choose additional rules. What do you do if it's your turn and there's no space there? So that's one way to make tic-tac-toe interesting. Here is another. It's called bidding tic-tac-toe. So imagine everybody gets $1,000. At the end of the day, this is monopoly money, so it doesn't matter. All that matters is who wins. And you start with $1,000. Whoever bids the most gets to move, and they give the money they bid to the other person. Okay? Another way of doing it is you give the money to a banker. So I have decided how much I want to bid for the first move. I need a volunteer who will tell me how much they want to bid for the first move.
$50.
$50. That is cheap. Right?
I'm part Scottish.
I'm sorry?
I'm part Scottish.
Oh, okay. I am Jewish, so I can say the Seinfeld jokes when his dentist converted to Judaism, if anybody remembers that episode.
Yep.
That's why it bothers him. So for $50, that's a low value. And if I bid even modestly, I could actually seize the center, which is truly valuable. I'm overbidding. I actually assumed you would bid $300, and I bid $700. So I get the center.
So you only get, so let me just ask you, you only get one chance at a bid? It's not like you bid back and forth and then you stop when no one wants to go higher?
Correct. You each have a secret bid, and then you go 1, 2, 3, reveal.
Oh, okay, okay.
And so if it's a tie, then what happens is nobody wins and you have to bid again.
Okay.
There's another version where you have a tie-break coin, and initially one person starts with it, and if there's a tie, whoever has the coin decides if they want to win the bid. If so, they give the tie-break coin to the other person.
Okay.
I hate this version of the game because it's no longer completely symmetric. In this version of the game, there is no advantage for being first or second. There's no difference at all. So I have just spent $700 for the first move. So I only have $300 left, and you now have $1,700. I know how much I'm going to bid for my second move. I need somebody to tell me how much they want to bid for the second move.
301?
301. So I chose to bet $100. You would have actually beaten me. And I'm assuming you made a small bet of just 99. So I have 2 in a row. Does this look like I'm doing well?
Spending money.
I'm spending a lot of money. How much money do I have left at this point?
200?
700 on my first turn and 100 on the second.
Oh.
200?
I only have $200 left. I only need to win one more. But if you can win the next 3 moves, you win the game.
Ah,
How much should you bid for the next one?
100.
201.
201.
201. You know I'm going to be betting everything I have. Because if I can get the next move, I win the game. So I bet 200, you bet 201, you put an X there.
Ah,
Now I have $401. How much will you bid for the next one?
402.
402. And I just lose. And now, how much do you bid? Well, I have $802. You bid 804 and you beat me. I spent far too much money on those first 2 moves. So the question becomes, how much is that first move worth? What kind of results can we get? Now, one thing you can do is there's an easy answer. If you bet $1,000, that's clearly too much for the first move.
mm-hmm.
Can somebody give me another number that's clearly too much?
900.
900.
Yep.
In fact, we know 800 has to be too much because after $800, I had the first 2 moves and I wasn't able to win. We know 800 is too much. How low can we go? Just to make the math a little bit easier, we'll assume that if it's a tie, player 1 gets the move. And so I'm not going to go through all the algebra here. If anybody is curious, I'm happy to go through it later. But you can find at the end of the day, you bid more than 750 roughly, you're going to be in trouble, and the other person will be able to do 3 in a row. So you can just go down and just see what the different moves are. So what I like about this is it takes a classic game, which everybody has seen, and comes up with a way to make it a little bit more interesting. Now, there are other things we can do. I should have an advantage over you in this game. Why? So what's my biggest advantage over you?
You played before.
I've played before.
Yep.
Or if you're playing against, a kid who is maybe 5 or 6, you might have a grasp of mathematics. Can anybody think of how you might be able to handicap yourself in this game?
Less money?
Yeah, you could take less money or you could give the other person more money. So if you have more experience or if you're older and taking more math, you might say, I'll take $1,000 and you can take $2,000. You can try to find like a nice handicap like golf or tennis. Okay. So shifting games, the rectangle game. So unfortunately, when I do this in schools, I would love to bring in a Hershey bar and physically break a Hershey bar, but that violates our no food in the classroom policy. So sometimes I can actually bring Hershey bars and give them out afterwards for the kids to eat at home. The way it works is you take an M by N board, and on each turn, you can break along a horizontal or along a vertical. To break wins. Does someone have a winning strategy? So what is it? And does it depend on the size of the board? I've done this a lot in 3rd grade classes, and they do a phenomenal job. What we do is we have them play lots and lots of games, and we have them gather data. We have them record what was the length, what was the width, who went first, who won. And they start to notice patterns. So in an ideal world, we would actually split you up into a bunch of small groups. I would hand you out a piece of paper, play a bunch of games with each other, and try to get some data. Given, all the stuff that's going on, we're going to just... So I'm going to just show you, here's a possible game. So it goes first and breaks it all the way down like this. So you have to break going from start to end. You can't stop partway down. Now on blue's turn, blue can be one of the 3 remaining columns, or there are 4 rows here, and there's 4 rows on the other side. You can't cross a solid line. For instance, maybe blue does that. And then maybe red does this. So the biggest mistake, the biggest issue kids have when they try to do this is they would have the blue line maybe going all the way across through the red line, or maybe stopping over here. You have to make sure they play correctly. So blue goes here, red goes there, blue goes there, red, and so on, and so on, and so on. So you can play lots of different boards, different sizes, try to find out if there's any strategies. Okay? And so here's a couple of bits of data. So we had a huge number of people play, and on every 2x2 board, player one always won. On every 2x3 board, player one always won. Maybe player one always wins, but no, on the 3x3 board, player two won every single time. On the 2x4 was always player one. The 3x4 was always player two. The 4x4, I'm sorry, the 3x4 was always player one. The 4x4 was always player one. The 3x5 was always player two. Can anybody see a pattern? So can anybody see a pattern on when player one wins or when player two wins?
If the area is odd, player two wins. Even
Wonderful
one wins.
conjecture. If it's an odd area, player two wins. And so when my daughter and I did this earlier in the year in the 3rd grade classroom in the neighboring town, she was very insistent that we do not lie when we talk to the 3rd graders. And so what I can't say is, I was very careful. I said, well, I'll let you choose. Do you want to go first or second? Because you haven't played before. And if they say they want to go first, then I draw a board that's odd by odd. If they say they want to go second, I draw a board that has an even area. And so I want to show you how we can prove that this conjecture is right. And it uses one of my favorite concepts in mathematics. It's called a monovariant. An invariant is something that's always fixed, always has the same value. You think of your physical constants. And a monovariant is something that changes in only one direction. If you have taken physics, entropy disorder only increases over time. You would not take a bunch of shards of glass and drop them and all of a sudden have a nice vase emerge. But you can't have a nice vase go over the edge and become a bunch of shards of glass. So the idea is to associate a monovariant to the rectangle game, a quantity that only moves in one direction. Let's take a 2x3 board. So our conjecture is player one should win. And what we notice is every time we move, we increase the number of pieces by one. If we move 0, we have just one piece, the initial board. We then move, and it's the same as breaking the board into 2 pieces. So after one move, there are 2 pieces. We now move over here, and there's now 3 pieces. We move over here, there's 4 pieces, 5 pieces, 6 pieces. And so the number of moves we have is 1 less than the number of pieces. And so then you can just figure out, do you end up on player 1 or player 2? And since player 1 starts, if there's an odd number of moves, you will end up with player 1. If there's an even number of moves, you will end up with player 2. And that's the complete analysis of the game. So this doesn't use any high-level mathematics, but what it does use is looking at the problem the right way. It's this beautiful quantity that only moves in one direction. Okay, so if we have an m by n board, just doing it more mathematically, the number of moves is mn minus 1. And so if mn is even, then player 1 wins, else player 2 wins. So I'm going to now take this idea and associate it to another game, the zombie game. For those of you who are struggling dealing with the coronavirus, I do apologize for apocalyptic slides now. This was prepared in better days. So one of my favorite quotes is the hammer. And there's many formulations. One of them is, if all you have is a hammer, pretty soon everything looks like a nail. And there's a lot of ways to look at this. If you're good at something, you find a way to take whatever somebody gives you and recast it to your strengths. Another way to look at it is, if you have a hammer, go to the land of the screwdrivers. Because if they could have solved the problem with the screwdriver, they would have. They don't have the right tools. So I've actually written papers in not just math, but in statistics, physics, marketing, economics, accounting, geophysics, baseball, all these different fields, because I can take what I've learned in math and apply it in different settings. You just have to tell me what the things mean. That's one thing I love to emphasize to my students. So here are the rules. And again, I do apologize if this is too close to home. If you share walls with 2 or more infected people, you become infected. Once you are infected, you are always infected. So imagine over here we have this initial configuration. So the red cells are infected. Are any cells infected in the next level? Are any cells adjacent to 2 infected cells?
Yes.
Yes, which one? Give me row,
Row 2, column 3.
row 2, column 3. Anything else?
Row
Row 1,
1.
column 2.
Yeah.
Right. So anything other than those 2 get infected initially?
No.
Just those 2. Now at the next level, is there anything that's now adjacent to 2 infected cells?
Row 2, column 4.
Row 2, column 4. Anything else?
Row 3, column 3.
3,
No.
column 3.
Yeah.
Okay. Anything else now?
Top right.
Top right. And then down here as well. Anything else? And that's it. Nothing else is adjacent to 2 infected. You have to be sharing a whole wall. Sharing a diagonal through this does not count. So this one only shares with this one. This one only shares with that one. The zombie apocalypse is contained. More than half of our population has been infected, but at least we've contained it. So here is my first question to you, and I don't care how smart-ass of an answer there is. Give me an initial configuration of infected cells that ensures that eventually everybody's infected. The simplest configuration that makes sure everybody's infected.
Diagonal.
No, you're being too smart. The simplest.
All of them are infected to begin with.
Yes, infect everybody. Extreme cases. I love going for extreme cases. If you infect everybody, then eventually everybody will be infected. In fact, they're infected originally. This is very wasteful. For an n by n square, it means we need n squared zombies initially. Can somebody give me something that's a little bit better than every cell?
Every other cell?
Every other cell. So if we do every other cell, that saves 50%. And then in one moment, we will get everybody. So we've gone from something of n squared to something of 1/2 n squared. That's a great savings, but it's still growing like n squared. So the question is, can we make it significantly smaller? And now the answer of the diagonal comes into play. So if we infect the main diagonal, then one turn later, we get the diagonal above and below. And then in another turn later, we get the diagonals above and below that. And you can see the infection spreading until everybody's infected. That only requires n infected cells to begin with. So we've gone from n squared to 1/2 n squared to n. And what I like is this shows students the level that you can actually have different quality results. Can we do better than n? Is it possible to have n-1 infected and have that propagate everywhere? And the answer is no. And I'm going to show you why by using this idea of a monovariant. So imagine the 2 red cells are infected and these white cells over here are not. So the cell between them is going to be infected. So does everyone agree that this cell becomes infected?
Yes.
Let's look at the perimeter of the infection. Because this white cell was not infected initially, we're assuming that only 2 of its 4 neighbors are infected. We lose this wall, we lose this wall, but we gain these 2 walls over here. So the perimeter of the infection hasn't changed. If we have just these 2 cells infected, we see again the perimeter doesn't change. We lost 2 walls, we gain 2 walls. Over here, we have 3 cells, 3 neighbors that are infected. We lose 3 walls and gain 1. The perimeter decreases by 2. And in this case, the perimeter decreases by 4. So the perimeter can never grow. So imagine you start off with n-1 cells that are infected. The maximum perimeter would be, if they never share any walls, it would be 4 times n-1 or 4n-4. What is the perimeter of a square that's n by n?
N squared.
Nope, that's the area.
Oh, sorry.
4n.
4n.
4n?
4n. And so since the perimeter never increases and the perimeter of an n by n squared is 4n, there must be at least one square that's safe. Is it possible there's only one square that's safe? So could I have like a 5 by 5 board with just one cell safe? So is it possible for one of the cells to have only one neighbor? Or does everybody have at least two neighbors?
Everybody has at least 2.
Everyone has at least two neighbors. So if only one cell was safe, since every cell has at least two neighbors, it would have to neighbor two cells that are infected, so it would have to be infected. So even though the proof only tells you that one square is safe, we can immediately conclude that two squares must be safe. Now, I'll leave it for you as a problem to think about, must there be a row or a column that's safe? And again, what I like about a problem like this is sometimes if you just get a little bit of information, you can milk it and push it forward and get a lot more. And there's a lot of great questions you can ask students to think about. You could also try playing this on a different shaped grid. What if you played it on something that was hexagonal? And the idea is to encourage students to try to explore this. The next is the I Love Rectangles game. So here's the way the I Love Rectangles game works, and I don't know why there's some issues with the printing at the top. It is not some secret code. So we have a table, and we have a 1 by 1, a 2 by 2, a 3 by 3, a 4 by 4, a 5 by 5, a 6 by 6, etc. You have each n by n square once and only once. And I've actually made these out of plastic, and I bring them with me to the elementary school. My job is to form a rectangle that has more pieces than my rectangle. And here's the rules. You can't put a piece down on top of another. You put the pieces down one at a time. And your shape must always be a rectangle. So I tell the kids I'll give them $20 if they can do better than I can. In fact, I'll give you $20 if you can put down 2 squares. Is it possible to put down 2 squares? So at every moment in time, your shape must be a rectangle. So let's say you put down the 3 by 3 square first. That's a rectangle, so that's fine. Can you put anything next to it? So could you put anything next to the 3 by 3 and still have it be a rectangle? Remember, you only have one of each square. So is there anything you could put down next to the 3 by 3 that would keep it as a rectangle? Could I put the 4 by 4 next to it?
No.
No, the sides don't line up. What about the 5 by 5?
No.
What about the 2 by 2?
No.
If I want it to be a rectangle, it has to have a side of length 3, but I only have one 3 by 3 square. So there's nothing I can do. So does everyone agree that this is a boring game? So let's make the game a little bit more interesting. I have to give you more pieces to play with. What's the smallest amount of additional pieces I could give you?
3.
I'm sorry?
3.
So I can't give you less than 3 pieces? The fewest is if I give you one more piece, right? And what's the smallest piece I could give you? I could give you another 1 by 1.
Mm-hmm.
So now imagine you have 2 1 by 1s, a 2 by 2, a 3 by 3, a 4 by 4. Can you put down 2 pieces now? So what two pieces could you put down and form a rectangle?
The first two?
The first two. And now you would have a 2 by 1 rectangle. Is there a piece to put down with a 2 by 1 rectangle? What could we add to the 2 by 1 rectangle?
To keep it a rectangle,
Well, look at all the different squares we have.
put a 2 by 2 by it.
Put a 2 by 2 down by it. Now we have a 2 by 3 rectangle. What could we put down?
3 by 3,
A 3 by 3. Now we have a 3 by 5. What could we put down?
5 by 5.
5 by 5. So the sequence is 1, 1, 2, 3, 5. Does anybody
Fibonacci.
recognize the sequence?
Fibonacci.
This is the Fibonacci's. This is a way to have the students discover the Fibonacci numbers. They're going to spiral out. So there's a great video on a lot of applications and instances of the Fibonacci numbers. My daughter and I, a couple of years ago, with a little help from my son, made the Fibonacci spiral out of fuse beads. This is from a cube that I made from a Fibonacci conference.
That's cool.
So I actually was stopped by security and they wanted to look at the cube. I said, I'm willing to spin it around in any direction you want. I'll turn it, but please, it took me a lot of time to adjust it like this. They were good sports. So here's the Fibonacci spiral. And there's a beautiful theorem that's lurking here. And so I'll go back a little bit over here. So we have 1, 1, 2, 3, 5. What's the area of a 5 by 5 square?
25.
25. So what you notice here is there's two ways to calculate the area of the rectangle. It's length times width, which is 5 times 8, or it's 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared. So what this is telling you is that the sum of the first n Fibonacci numbers squared is equal to the nth times the nth plus first Fibonacci. It's a geometric proof. 1 squared plus 1 squared plus 2 squared plus 3 squared plus 5 squared plus 8 squared is 8 times 13. So there's a lot of wonderful stuff you can do with the Fibonacci spiral. And so these are just some of many games. For the next one is the I Love Triangles game, I think, which I will not do today. And I'll save that for next time. I want to be mindful and make sure we have a little bit of time for discussion. Are there any comments from this part before we just have a final wrap-up session?
No.
I think my algebra students that struggle with math would really enjoy doing some of these games.
So what I love about these games is these are hands-on, especially with the I Love Rectangles at the end, where you are physically putting down the tiles. If you have Legos, you can actually make these out of Legos. You can use some nice paper, and then they can physically play with them, and they will come up with the Fibonacci spiral. And I've done this all the way down to kindergarten, and in kindergarten, the kids have found that this is how they do it. I'm going to do all the algebra with them in kindergarten. If your kids are a little bit older, if your students are a little bit older, there's a lot of wonderful things that you can do with this. The other thing is, similar to the tic-tac-toe, is to just emphasize to them the power of looking at old things in new ways. That just because we've played tic-tac-toe this way for so many times, maybe there's a way we can make the game fun. And now all of a sudden it's unclear what's the right way, what's the best strategy, how should we do things? And you can have handicaps, and then you can kids come up with your own way of making tic-tac-toe fun. You could start off with a larger board, maybe 10 by 10. Maybe you're trying to get 4 in a row. Whoever goes first has an advantage. So maybe you have a couple of O's deep, far away from the center. So if the game lasts a long time, now the person has a bit of an advantage. And just anything that I can do to give my students an opportunity to think creatively and not just go through all the problems that we have to have them go through so that they can do well on the MCAS. I love that exam. I think it's wonderful that we have it. Hi, all the people who are listening. But we often don't give the kids a chance to be creative and explore and have fun with math. And so as much as possible, I think these are wonderful opportunities. The mono invariance from the zombies is another wonderful example of a terrific math concept. It's often hard to think of the right thing to look at the perimeter of the infection. That's fascinating. I mean, how do you think to look at that? But once it tells you, you can follow the algebra. And if you're interested in stuff like this, there's other problems similar to this that I can share with you where you do use these concepts. So I'm going to end the meeting now, and then I will start it again in about 1 minute.